Hi, I'm Brian Pruitt, tutoring high school physics. Today's topic, wave interference and standing waves. Wave interference occurs when two waves are traveling along the same medium and they meet each other. So here we have two peaks coming along, they're traveling in opposite directions and they meet each other. They'll build on each other to form one big peak. Likewise, here we have two troughs traveling along in a medium and they meet each other. When they meet, they'll form one big trough. This is known as constructive interference, when two waves meet and then build on each other. However, what if the opposite happens? What if a peak and a trough come together at the same time? Well, in this case, they'll cancel each other out, resulting in destructive interference. Now, this interference only happens for the moment in which the troughs, the peaks, or the peak and the trough meet each other. After this, the original peak and trough will continue on its way. After this moment of destruction, you'll see a peak coming off this way and a trough coming on this way. Here, you're going to see the two troughs of their original size heading off in their directions. Here, the two peaks in the original size are going to head off in their opposite directions after this moment of interference. But yes, that is what happens when they interfere. If they build on each other, it's constructive. If they cancel each other out, it's destructive. So next up, standing waves. What is a standing wave? Well, we're going to start visualizing one. First, let's start with an experiment. Let's say that you're holding one end of the string and the other end of the string is attached to a wall. If you whip the string once, a wave is going to form. It's going to go along, hit the wall, and then it's going to be reflected back at you. Now whip it twice. The first wave you send out is going to be reflected, and it's going to meet the oncoming second wave. And then they're going to interfere in some way. We're on our way to creating a standing wave. Now continuously whip the string. All the waves that you're sending out are going to be reflected, and then they're also going to meet the waves that you're still sending out. So basically, you're going to get continuous interference that's going to start happening, because all the waves that are being reflected by the wall are meeting all the waves that you're sending out, and then you're going to reach a more or less stable state that looks something like one of these. So let's say you continuously whip the string so that one big arc kind of forms, and it alternates between an up and a down stage. Or if you start whipping it faster, you can get to another frequency of whipping where you get two arcs forming, and then three arcs, so on and so forth. These are known as harmonics. The first harmonic, second harmonic, third harmonic, so on and so forth. Each progressive harmonic includes another arc. This is known as a standing wave, a part of a wave that is more or less constant, alternating between two states. So let's take apart a standing wave. There are two major parts to a standing wave, nodes and antinodes. Nodes are areas where there is utterly no motion. So you see these areas too, right here, there will be absolutely no motion. On a string, they won't move at all. They won't go up and down whatsoever. The antithesis to the node is the antinode, the point that moves the most. So basically, at the top of a peak or bottom of a trough. For the purposes of a standing wave, they're going to be the exact same thing. So this is actually going to be considered only one antinode, however. If we move up over here, we have 1, 2, 3 nodes. These parts are going to move at all. And we have 1, 2 antinodes. For our third harmonic, we're going to have 1, 2, 3, 4 nodes and 1, 2, 3 antinodes. So to quickly figure out how many nodes and antinodes your particular harmonic is going to have, the number of nodes is for the nth harmonic is n plus 1. The number of antinodes is just n. You're often going to be asked to calculate the frequency of a standing wave. To do that, we have this nifty little function here. The frequency of the nth harmonic is equivalent to n times the velocity of your wave divided by 2 times the length of the string. Or if you already know the frequency of the first harmonic, you can simply take n and multiply it by that frequency. So let's find the frequency of a first harmonic on a string that's 5 meters long and a wave speed of 5 times 10 to the negative 5 meters per second. So f sub 1 is equivalent to our n, which is just going to be 1, times our v, 5 times 10 to the negative 5 meters per second. And we're going to divide this by 5 meters times 2. So we get 5 times 10 to the negative 5 meters per second, divided by 2 times 5 is 10 meters. And so that's going to leave us with 5 times 10 to the negative 6 hertz. And so then here we have the first harmonic for this particular string. Now we could then use this to find any other harmonic by multiplying it by n for that nth harmonic. Alright, to recap. When two waves are traveling along in a medium and they meet each other, interference happens. If they're building on each other, that's known as constructive interference. If they cancel each other out, that's destructive interference. After the bit of interference, they'll then move on unhindered by each other. This is used in the generation of standing waves. If you're holding one end of a string and the other is attached to a wall and you whip it, a wave will be sent out and then it will be reflected by the wall. If you keep whipping it at a constant frequency, you'll eventually find certain frequencies where you'll find sort of a constant wave motion. You might have 1 arc, 2 arcs, 3 arcs, so on and so forth. Each progressive increase in number of arcs requires an increase in frequency. These are known as harmonics, more or less constant states of waves. The first harmonic has 1 arc, the second harmonic has 2 arcs, so on and so forth. These standing waves will have nodes and antinodes. Nodes are parts of the string that aren't going to be moving at all. Antinodes are parts of the string that are going to move the most. For the nth harmonic, the harmonic has n plus 1 nodes and n antinodes. To calculate the frequency of a standing wave for the nth harmonic, the frequency of the nth harmonic is equivalent to n times the speed of the wave divided by 2 times the length of the string. Or if you already have the frequency of the first harmonic, it's n times that frequency. Alright, that's all for now. Again, I'm Brad Preer. See you next time.